Hello, everyone, and welcome to our deep dive into the mathematical engine behind artificial intelligence. Today, we're uncovering the crucial role of calculus in how AI models learn and optimize themselves. It's not just about complex equations, it's about understanding the intuition that drives innovation in AI. By the end of this lesson, you will be able to, first, understand derivatives as the fundamental measure of change in AI model performance. Second, you'll learn how AI systems implement numerical derivatives to handle complex real-world scenarios. Third, we'll demystify gradient descent, the core algorithm that teaches AI models to get better over time. And finally, you'll be able to visualize this powerful learning process, giving you a tangible sense of how AI truly optimizes. Let's get started. Imagine you're trying to fine-tune an AI model. How do you know if adjusting a parameter, even slightly, will make its predictions better or worse? That's where derivatives come in. In AI, derivatives tell us exactly how much our model's performance changes when we tweak its internal parameters. Think of it like adjusting the volume knob on a radio. If you turn it clockwise, does the sound get louder or softer? And by how much? The derivative provides that immediate feedback. It's like having a compass that doesn't just point north, but points directly toward the direction of improvement for your AI model. This fundamental concept is what allows AI systems to intelligently navigate their way to optimal solutions, step by step. Without this compass, AI would be guessing in the dark. While the idea of a derivative is clear, real-world AI models often deal with incredibly complex functions that don't have a simple, neat mathematical formula for their derivatives. This is where numerical derivatives become essential. Instead of finding an exact formula, we approximate the derivative. Think of it like how your GPS calculates your current speed. It doesn't have a direct sensor for speed. Instead, it compares your position at one moment to your position a fraction of a second later. The change in position over that tiny time interval gives you an approximation of your speed. Similarly, AI frameworks use methods like the difference quotient to calculate the approximate slope of a function by evaluating it at two very close points. This approximation is incredibly powerful because it allows AI to learn even from functions that are too intricate for analytical solutions. It's the practical bridge between theory and real-world AI implementation. Now, let's bring it all together with gradient descent. This is where calculus truly becomes the magic behind AI learning. Imagine you're hiking down a mountain in thick fog, trying to find the lowest point. You can't see far ahead, but you can feel the slope directly under your feet. Gradient descent is exactly like that. It's the core algorithm behind all neural network training. It uses derivatives to find the minimum of a function, which in AI terms means minimizing the model's prediction errors, also known as the loss function. At each step, the model calculates the gradient, the direction of the steepest ascent, and then moves in the opposite direction, effectively following the slope downhill. It iteratively adjusts its parameters, taking small steps until it reaches the bottom of the error landscape, where its predictions are as accurate as possible. This simple yet profound process is how systems like GPT, DALL-E, and autonomous vehicles learn and improve. We've covered some powerful ground today. Let's quickly recap our learning journey. We started by understanding that derivatives are the compass for AI, quantifying how model performance changes with parameter adjustments. We then explored numerical methods, appreciating how AI approximates derivatives for complex functions, much like a GPS estimates speed. Crucially, we grasped gradient descent, the optimization engine that allows AI models to learn by iteratively minimizing errors, always moving downhill towards better performance. Finally, we visualized this learning path, seeing how these concepts translate into tangible improvements. You now possess the mathematical intuition that separates AI practitioners from mere users. You understand how the learning happens under the hood. To test your understanding, consider this. How does understanding derivatives help you in debugging an underperforming AI model?